Hi, this is Mrs. Cribb, and we're going to go through some of the notes for Chapter 5. So you need to pull your notes out right now if you haven't got them out already. Excuse me. And I'm going to just review a little bit about atomic radius. We should have already learned this by now, but we've already talked about atomic radius and how, if we look at this picture, it starts right here where it's large, and it gets small as we go to the other side. And that's as long as it's in the same period. So like this would be period 1, 2, 3, 4, 5, and 6. And so if we look at period 4 right here, potassium has 4 energy levels, but so does calcium and gallium and germanium and arsenic and selenium and bromine and krypton. But as we go across, we have more and more electrons and more protons. And so the charges pull each other tighter and tighter and tighter. Think about the rubber bands around the watermelon again. We have a lot more positives on this side, a lot. And we have a lot more negatives over here. And so they're very strongly attracted to each other because opposites are attracting. On this side, even though they have the same number of energy levels, they only have a couple of positives and negatives. So they're attracted, but not as strongly. These guys get pulled in very tightly because opposites are strongly attracted to each other. They get squeezed tightly, so they get smaller as they go across. And then as we go down, they automatically get bigger because we're adding more and more energy levels. This has 1 energy level, so like the nucleus would be in the middle. This has 2, so there's the first and then the second. This one has 3, so there'd be 3 energy levels. And as we get more and more energy levels, it gets larger and larger and larger until we get down cesium, and francium is even below this. And it has 7 energy levels. And I drew the pictures of the 4 models for these atoms. I'm not going to redraw those right now, but you can refer back to your notes for those. And then ionic radius, we talked about this as well, and that cation ions are positive ions and anions are negative, and the cation ion is smaller. Let's see, there's a cation is usually smaller because they lose an energy level, and the anion is larger than the parent ion because they have those extra electrons that are repelling each other in the outer shells, kind of getting away. They're spreading out the atom's electron cloud, and also they're shielding each other, protecting each other from the positive nucleus. So the nucleus can't pull them in as tightly. So that brings us to ionization energy. The first ionization energy is the minimum energy required to let's see here, remove the first electron from its outer shell to make a cation. To make a cation. The minimum energy to remove the first electron from its outer shell to make a cation. It increases from left to right, so it goes up from left to right. So before it went down, the size went down, but the ionization energy goes up. And remember, the radius is smaller, so the electrons are closer to the protons in the nucleus, and this makes them harder to pull away. Opposites are attracting. Now, we're going to consider the nucleus a mama, okay? And all the electrons are babies. So, baby electrons, mama nucleus. And the mama nucleus won't let you take her baby. So think about it like this. Here's mama nucleus in the middle with her mama nucleus is a proton, bunch of protons, and she has an electron really close to her. And there's an attraction. Mama nucleus is holding on to this baby tightly. And so if somebody comes along and tries to take that baby, she's going to fight him. It's going to take a whole lot more energy because she's holding tightly. Think of a mama and a baby in a stroller. And if somebody tries to come and take my baby out of my stroller, I am going to put up a fight. Okay? But the farther the babies are, the electrons are from the mama, the easier it is to take them. So think of a mama sitting on a bench and the babies are way off on the other side of the playground, maybe playing on one of the swings, or and she's just kind of looking around. She has a lot of babies, so she's looking around, but that one's real far away. And when somebody comes and tries to steal that baby, she might yell, but they can grab him and run without having to put up very much of a fight from her. So it's just an analogy, but think of it that way. All right, so ionization energy is the amount of energy it takes to steal that baby electron. And if the baby electrons are close and held tightly, it's going to take a lot of energy. If the baby electrons are far away, it's not going to take much energy at all. So the ionization energy decreases as we go down because the size of the atoms are getting bigger and bigger and bigger. So the higher energy levels are farther away, making the electrons easier to pull away. Mama nucleus is getting farther away from the baby electrons. She's so far away you can't get to them, and the electron napper comes along and takes it away. Oh, the horror. Okay? That's just an analogy. So before I go on to electron affinity and electronegativity, I'm scooping down here below the notes to the periodic table. So let's just look at a couple as far as ionization energy goes. So look, here's poor old francium. Francium, atomic number 87. Francium, 7 energy levels. Okay, so imagine that. Here's mama nucleus, and then 7 energy levels. 1, 2, 3, 4, 5, 6, 7. That is where her valence electron is. There it is. And now, francium is in column 1, or 1A. That means francium has one baby out there very far away. Okay? Now let's think about that. See how big francium is? See, sodium, if I look at sodium, so this is francium. Okay, let's look at sodium. There's the nucleus, and sodium has only 3 energy levels, okay? 1, 2, 3. And sodium's one valence electron is also sitting out there. Now, which one's larger? Where are the babies the farthest away? Francium's baby is the farthest away. Okay, let's look at that. From here to here, that's farther away than from here to here. So which baby is easier to take? Well, much easier to take this little baby here from francium, that electron, because it's so far from the mama, she can't fight back so much. Sodium, it's not so easy to take it. I mean, you can take it, but it's harder to take sodium's electron than francium's. So as you go down and it gets larger, it gets easier to take the baby electrons, less energy is required then to do it. Less energy. Now what if we go across the chart? So let's now look at, we looked at sodium, so let's look at argon, okay? Argon has 18 electrons, 18 protons. So argon's well, first of all, argon's going to be super hard because it's a noble gas, and it has 8 valence electrons, and so it's super happy and doesn't want you to have any of them. So I will look at chlorine though. Both of these guys, ionization energy are really, really big. So here's chlorine. Chlorine, and it's in period 3, just like sodium. So see there, energy level 3, period 3. So 3 valence, 3 energy levels, 1, 2, 3. Now chlorine is in column 17, or 7A. So it has 7 valence electrons. I can draw 1, 2, 3, 4, 5, 6, 7 electrons in that 3rd energy level. Okay? Now, its electrons seem to be just as far away from the nucleus as sodium, but it's not. And that's what the radius was about. See, chlorine has 17 protons and 17 electrons. Think of that as 17 rubber bands. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Pulling in tighter and tighter and tighter. Sodium has only 11. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 rubber bands. Well, the 17 rubber bands are squeezing tighter. So really, even though it seems like they should have the same size, chlorine is actually a little smaller. Chlorine is smaller than sodium. The sodium would be larger than chlorine. Okay? So that means the babies are closer. So the ionization energy, bigger ionization energy. Ionization. There we go. Energy. If it's a smaller atom, it has bigger ionization energy. So see how those are opposites? Smaller atoms have bigger ionization energy. Why? The babies are closer to mama. Larger atoms have smaller ionization energies. Why? The babies are farther from mama. Hard for them to attract each other. Mama cannot fight back. Now what it really is the positive protons and the negative electrons being attracted, because opposites attract. But when you think about it, is how far the babies are from mama nucleus. So let's go back up to your notes. And so that brings us to electron affinity. Affinity means I like something. So I have an affinity for chocolate. I have affinity for pumpkin spice lattes. But here, it's the amount of energy required to add an electron to a neutral atom to form a negative ion or an anion. So basically, I want to add an electron to an atom, and how much energy is going to be required. And some things will say the energy that's released when that's done. But how much energy is required to add that electron to an atom? Okay? This is the opposite of ionization energy. Okay? What is ionization energy? The amount of energy required to remove. So what is the electron affinity? Required energy to add. Okay? Mama Francium already has 87 babies. Okay, let's think about poor Mama Francium again. 87 babies. Let's draw them again. Here's Francium, Mama Francium. 7 energy levels. 1, 2, 3, 4, 5, 6, and 7. Make sure that, these are really circles that go all the way around. Inside all these circles are 87 electrons. And she only has one more electron right here. Okay, that's the valence one, right? It's far away from Mama, so it's easy to take it. Now, is it easier to remove one electron or gain 7 more? Remember, we want that octet. Well, it's easy to remove it. It's easier to remove it. So because it's easier to remove it, she will gladly let you adopt one of her babies, because really, she does not want any more. She's already got 87. Do not make her have 88. If you take one, now she only has 86. In fact, if you take one, she goes down, she loses that 7th energy level. Take that valence electron, adopt it from her. She loses it. Now she's a little bit smaller, and the babies are a little closer to her. In fact, she has 8 valence electrons in the outer shell, and now she's happy. Remember, they want 8, the octet. So please do not give her another baby. It does not help her to have 88 electrons. Okay? So electron affinity measures how strongly atoms attract additional electrons. She does not want additional electrons. She wants to get rid of her 1 electron. For incomplete sublevels, remember S, P, D, F are the sublevels. Most elements will easily take the additional electrons. They want to complete their octet. Okay, so if it's SP1, it would love to be SP2, because remember, S has 1 shape. Why did I say SP? If it's 1S2 or 2S2 or 2S1 rather. Always SP's later. Okay, if it's 1S1, it would love to become 1S2. Remember, the S sublevel has 1 shape. That's that sphere. And it can hold only 2 electrons, and that would be all it could hold. It would be complete. So it would gladly do that. And so the 2s2 and the 2p6 work the same way. Okay, electronegativity is the measure of the attraction between the nucleus and the valence electrons. In most cases, it's determined for atoms bonded in molecules which share electrons. So we're talking here about covalent molecules, things that are sharing electrons, and we'll learn more about that later. So there's another difference. Electronegativity is very important, and it's talking about attraction between the nucleus and valence electrons, and it's talking about bonded electrons that are being shared. Affinity is talking mostly about unbonded atoms. And that's a difference, okay? Affinity is talking about unbonded atoms. Electronegativity is talking about bonded atoms and how much they're sharing their electrons. Really, it's a measure of an atom's ability to attract and hold electrons in a molecule, and it's determined experimentally or mathematically. Okay? Fluorine is the most electronegative element on the chart, and it really wants to complete the octet. Now let's look at the chart real quick. All right, I'm going to stop this real quick and do some fixing. All right, here we are. So let's find fluorine. There it is, fluorine. All right, let's talk about fluorine. Fluorine has 9 electrons total. It's in energy level 2. So remember, second period, go all the way across. See how it feels, the 2s, 1 and 2. This would be the 2s2, and this is the 2p, the 2p1. This is all the way to the 2p1, 2, 3, 4, 5. Okay, so it has 7 valence electrons, because 5 from the 2p and 2 from the 2s. 7 valence electrons because it's in group 7a or 17. It's the smallest atom with 2 energy levels that has 7 valence electrons. That makes it the strongest atom on the chart. Fluorine is the bully. Fluorine can take anybody's electron from them. Fluorine will take electrons from oxygen, from chlorine, from any other place. Okay? These guys on the other side, they are not very electronegative. They are willing to give them up. So let's go back up and draw fluorine for a second. All right? Fluorine has 9 electrons. We have 2 in the first energy level. That's energy level 1, and that would be the 1s2. And then we have 7, 1, 2, 3, 4, 5, 6, and 7 in the second energy level. And that'd be the 2s2 and the 2p5. 7 valence electrons. We only have really one spot right here where we need another electron. Remember, we want 8. We want the octet. So fluorine is badly looking for an octet. Fluorine is small, only 2 energy levels. 1, 2. And so those electrons are close. The electron babies are close to the mama. Fluorine is holding them tightly. So you can't take the electrons from fluorine. So let's think. Fluorine is small. Fluorine has a large ionization energy because it's so small, because the babies are so close to mama, because you can't take them. Fluorine has a large electron affinity and electronegativity. It's so strong, it will take them from anybody. Everybody else will be positive compared to fluorine. And if you look at the chart, okay, if we talk about electronegativity and electron affinity, we can look at some trends, and I'm going to write them on here. If you start down here at francium with 87 babies, and you point up to fluorine with only 9 babies. Okay, this is the most electronegative. Most En for electronegative. And francium would be the least electronegative because it's large and it does not want electrons. It wants to get rid of them. Fluorine is small and it really wants one more, and it's really strong. So the closer the elements are to fluorine, the more electronegative they are. The more they want electrons, and they usually also means the more electron affinity they have. So the closer it is to fluorine, the larger the electronegativity gets. Now what about size? Size is the opposite. Fluorine is the largest, okay, in size. Fluorine and helium are the smallest in size. So, opposite. The closer you are to francium, the larger you get in size. The closer you are to helium, the smaller you get in size. So oxygen, what about oxygen then? Oxygen's right here. Oxygen is pretty small because it's close to helium, and it's very electronegative because it's close to fluorine. In fact, oxygen is the second most electronegative element, and it's always negative. That means it always sucks in some electrons unless it's stuck to fluorine, because fluorine is still the ultimate bad guy when it comes to electrons. Okay, fluorine still will take it away. So that deals with size and electronegativity and pretty much electron affinity as well. Okay, so let's go back up. Let's do some checking. This is the problem from a textbook. So which element is more, just using these ideas, more electronegative? We have nitrogen or phosphorus? And I'm just going to have to scroll down really quickly to that chart. Nitrogen and phosphorus. So let's look at them. I'm going to pull them up, or use one of my colors here that might stand out. Nitrogen. Let's find nitrogen. Oh, there it is. There's nitrogen. And now we're going to find phosphorus. Was that the one I had? No, it's because that one's just, no. Oh, phosphorus, not fluorine. Phosphorus. Nitrogen or phosphorus. Okay, here they are. All right, which one's more electronegative? Well, which one's closer to fluorine? Or which one is smaller? Nitrogen. Nitrogen is 2 steps from fluorine. Phosphorus is not too far, but phosphorus is bigger. It has 3 energy levels, and nitrogen only has 2. The bigger it is, the farther the electrons are from the parent atom, the nucleus, the mama, the easier they are to take, the less they're held onto. So in this case, nitrogen is more electronegative than phosphorus. Okay? Nitrogen. Which one is more electronegative, rubidium or iodine? Okay? Quickly get down to the chart. Rubidium or iodine. Whoops, that's not iodine. Rubidium or iodine. All right, this one's a lot easier. Iodine is very close to fluorine, so it's definitely more electronegative than rubidium. Rubidium only has 1 valence electron because it's in column 1A. Very much wants to get rid of it, does not want to take them. It is not very electronegative. So iodine. Okay? Those are the reasons why. Now we have some additional problems here, so I want you to pause the video, look at your periodic chart, and then see if you can figure these out. All right, I've circled all the answers now, and I'm not going to flip back and forth for the periodic chart, but you should be able to look at it. Look at yours. So titanium is larger than gallium, of course, because titanium is element number 22, and gallium is number 31. Titanium has fewer electrons, but they have the same number of energy levels. So if it has more energy levels, it's bigger, but they have the same number of energy levels, so titanium is larger. Magnesium or phosphorus? Magnesium and phosphorus are both in period 2, but magnesium has fewer electrons, so magnesium is larger because phosphorus electrons and protons are pulled in tightly. Magnesium or barium? Barium has 6 energy levels. Magnesium only has 3. Barium's larger. Xenon or argon? Xenon has 5 energy levels. Argon only has 3. Xenon is larger. Okay? Larger electronegativity. Look up. Are they closer to fluorine? Oxygen's right next to fluorine. Now, it also has 2 energy levels and 6 valence electrons, so it only needs 2 more electrons. That's really why it's more electronegative than lithium, not just that it's closer to fluorine. Chlorine or magnesium. Chlorine is right under fluorine, so it's more electronegative. Chlorine has 7 valence electrons. Magnesium and chlorine both have 3 energy levels, but chlorine only needs 1 more. They're held tightly. They're small. Chlorine is actually smaller than magnesium, so it's more electronegative. Sodium or francium. Francium has 7 energy levels. Sodium only has 3. So sodium is more electronegative because it's smaller. Neither one of them are very electronegative. Okay, they both have 1 valence electron, but sodium's 1 valence electron is closer to its nucleus. Francium's 1 valence electron is very far away. So sodium is slightly more electronegative. Barium or beryllium. Barium has 6 energy levels. Beryllium has 2 energy levels. So that's wrong. Beryllium has 2 energy levels. It's a larger electronegativity because it's smaller. They both have 2 valence electrons. Okay? So now, which one has a larger ionization energy? Remember, the farther they are, the easier it is to take. So if it's a small atom, it has a large ionization energy. Small atom equals large ionization energy. So they're opposite. Why am I spelling that wrong each time? Ion is, well, I guess that was right. Ionization energy. Okay. So, here are the ones originally. Titanium's larger, so gallium has a larger ionization energy. Magnesium is larger, so phosphorus has a larger ionization energy. Barium is larger, so magnesium has large ionization energy, and then xenon is larger, so argon has a larger ionization energy. Okay, so that should finish up this portion of the notes. The next part will be on all the groups, 5C element families and their properties, and we'll do that in a separate video. I hope that helps. I'll see you soon.